Okay, so now what we're going to go through is look at these three techniques in working. So we're going to remove three links from a given graph and try to predict three links and analyze the performance of the link evaluation techniques. So we'll start with the preferential attachment technique. So given this actual graph, we're going to remove three links. Again, the same three links will be removed for every technique. Okay, so here I'm removing this example 4 5 1 2 and 1 5. So those are three links that are removed. So we'll try to now predict three links. Now the preferential attachment technique, the PAC score for a node pair is the product of the node degrees. So on this graph with the three links removed, we'll try to first find out the degrees of the nodes, and using them we can calculate the PAC score. So for node 0 the degree is 2, for node 1 the degree is 1, for node 2 the degree is 3, for node 3 the degree is 3, for node 4 the degree is 4, for node 5 it is 3, for node 6 3, 7 3. So those are the node degrees. Then, as I said, the PAC score is the product of the node degrees for the end vertices of the node pairs. So these are the node pairs that don't have a link between them in this modified graph. So for 0, you have a link with 1 and 2. So 0 doesn't have a link with 3, 0, 4, 0, 5, 0, 6, 0, 7. So these are the node pairs that don't have a link. Then 1 has a link with 0, of course that's counted for 0, 1. So 1 doesn't have a link with 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. Then 2 has a link with 0 but not with 1, but it's counted in the case of 1, 2. So just look at the higher IDs as we did in the previous example. So 2, 3, 2, 4 link is there. So 2, 5, 2, 6, 2, 7. Those are the node pairs that don't have a link. Then 3, 4, 3, 5 they have a link. 3, 6 and 3, 7 they don't have a link. Then 4, 5 don't have a link. 4, 6, 4, 7 is there. 5, 6, 5, 7 is there. 6, 7 is there. So everything is fine. So now for each of the node pairs, look at the node degrees that we have. For node 0 you have degree 2. For node 3 you have degree 3. So it's 2 times 3 is 6. That's the PAC score. Now for the pair 0, 4, again 2 times 4, which is 8. For pair 0, 5, it is 2 times 3, which is 6. So likewise, you find the PAC score for every node pair. Say for example, for 1, 5, it's going to be for node 1, the degree is 1, for 5, the degree is 3, so it's 1 times 3. Say for 2, 6, it is, the degree of 2 is 3, the degree of 6 is 3, so 3 times 3, which is 9. So for 4, 5, the degree of 4 is 4, the degree of 5 is 3, so 4 times 3, 12. So among all the PAC values, 12 is the largest. So the corresponding node pair 4, 5 is predicted to have the first link. So so we are trying to predict three links now. So the first link is predicted to be between 4 and 5. So we go ahead and add the link 4, 5, and on this modified graph, which I call as graph with one predicted link, I find the node degrees. And using these node degrees, now find the PAC scores for the other node pairs. Okay. So again, the only thing that changed between the previous degree values and now is for 4 and 5. 4 has now degree 5, one more link, and 5 has a degree 4. Okay. So that would change the scores wherever 4 and 5 are involved. So you have to be careful as we go change it. So it's better to just reevaluate all the PAC scores if you want to. So 0, 3, again it's 2 times 3, which is 6. Then 0, 4, it's going to be 2 times 5, which is 10. 0, 5 is 2 times 4, which is 8, and so on. So 2, 5 is 3 times 4, which is 12. So that is the largest value among all the PAC scores. And there's no tie. So we'll just say the pair 2, 5 is predicted to have the second link. Okay. So 2, 5 had here 9 and 4, 5 had 12. So that's why we went for 4, 5. So now because of the edge that node 5 got, the PAC score for 2, 5 went up, and now it is 12. That's the largest among all the node pairs that are out there that don't have a link yet between them. So 2, 5 is the second pair that is predicted to have a link. So now we update the node degrees based on this graph with two predicted links, and these are the node degree values. So the degree of 2 is now 4 instead of 3, and the degree of 5 is 5 instead of 4. So based on that, the node pair, what do you call, the PAC scores could change, especially if they involve 2 and 5 from the previous set of calculations. So again, just to make sure you're not making any mistakes, better to just reevaluate the PAC scores for all the node pairs. So 0, 3, it is 2 times 3, 6, 0, 4 is 2 times 5 is 10, 0, 5 is 2 times 5 also 10, and so on. So just we keep reevaluating. Now the pair 2, 6, it is 4 times 3, which is 12, 2, 7 is also 4 times 3, which is 12. So 12 is the largest among all the PAC scores, and there's a tie. Two links have the same largest PAC score. So we'll just say both the links are predicted to exist. So that's the third. Even though you are expected to predict only one link, since the two node pairs have the same largest PAC score, we just say both the links could be predicted to exist. So the third predicted links are 2, 6 and 2, 7. That is how I call it. So we say 2, 6 as well as 2, 7 have the third predicted link, or the third predicted links. So totally we have 4 links that are predicted, even though we expected to predict only 3. Because of the tie, we have predicted 4 links based on the JSE technique. And now let us compare with the actual graph before the removal of those 3 links. So this was the actual graph. So among the predicted links, only 4, 5 really existed in the actual graph. The other 3 predicted links, 2, 5, 2, 6 and 2, 7 do not exist in the actual graph. So the true positive is only 1, because only one of the links existed in the original graph. Then these 3 links that are predicted, 2, 5, 2, 6, 2, 7 does not exist in the original graph, so they are called false positive. Now we remove 3 links from the original graph, 4, 5, 1, 2 and 1, 5. 4, 5 has been predicted rightly, but 1, 2 and 1, 5 have not been predicted to exist. So the false negative is 2. So we saw this in detail in the previous video. So now using the true positive, false positive and false negative values, calculate the 3 performance metrics. So the critical success index is true positive divided by the sum of true positives plus false positives plus false negatives, which is 1 plus 3 plus 2, which is 1 over 6, 0.167. Precision is what proportion of the predicted links really exist. So the true positives divided by true positives plus false positives. So 1 over 1 plus 3, so it's 0.25. Recall is what proportion of the links that are expected to be predicted that are, or I can say that actually exist. What fraction of the links that actually exist are predicted rightly. So when I say actually exist, those are the links that actually exist and are expected to be predicted. Okay. So the denominator here for the recall is the links that are actually existing in the original graph and are expected to be predicted. So that is true positives plus false negatives. So one link actually was predicted rightly, but 2 of them were not predicted. So 1 plus 2 and the numerator is 1. So 1 over 1 plus 2 is 0.33. So now I'll continue with the AAC technique. So the AAC technique, the formula is summation of 1 over log n of k, which is the degree of the common neighbors. So if you remember the formula, so this is the formula. So for any node pair, we'll find the common neighbors and do the summation of 1 over log of the degree of those common neighbors. So let us see what we have here. So again, we remove the same 3 links. This is a graph with 3 links removed. So we'll find the neighbors for the nodes in this new graph. For 0 it is 1, 2, for 1 it is 0, for 2 it is 0, 3 and 4, for 3 it is 2, 4, 5, for 4 it is 2, 3, 6 and 7, for 5 it is 3, 6 and 7, for 6 it is 4, 5, 7, for 7 it is 4, 5, 6. So the number of neighbors is the degree, so this is 2 neighbors, so degree 2, so log 2 again to the base 10 is what we use, is 0.3010. 1 degree of 1, log 1 is 0 to any base, so any base, then it's 3 degrees, so log 3 to the base 10 is 0.4771, again log 3 to the base 10, log 4 to the base 10 is 0.6021, then this is all log 3. Then 1 over log degree, so 1 divided by these values. So when you take 1 over 0, it is going to be infinity, so you write infinity. Okay, so now what we're going to do is run through the atomic adder index for this, for one link prediction. So graph with the 3 links removed here. So these are the node pairs that don't have a link in this graph. So 0 has a link with 1 and 2, so no link with 3, 4, 5, 6, 7. 1 has a link with 0 but not with 2, 3, 4, 5, 6, 7. Then 2 has a link with 3 and 4 but not with 5, 6, 7. And 3 has a link with 4 and 5 but not with 6 and 7. 4 does not have a link with 5 but has a link with 6 and 7. 5 has 6 and 7. 6 has a link with 7. Alright, so for each of the node pairs, find the common neighbors. So for 0 and 3, we have 1, 2 as neighbors of 0. For 3, it is 2, 4, 5. So 1 is not here in 2, 4, 5, but 2 is here in 2, 4, 5. So there's only one common neighbor, which is 2. 0, 4, you have 1, 2 and 2, 3, 6, 7. So 2 is the common neighbor. 0, 5, it is 1, 2 with 3, 6, 7. So no common neighbor. 0, 6, 1, 2 with 4, 5, 7. So no common neighbor, and so on. Now 4, 5, you have 2, 3, 6, 7. 5 is 3, 6, 7. So 3, 6, 7 are the common neighbors. 3, 6, you have 2, 4, 5. 4, 5, 7. So 4, 5 is a common neighbor. So once you find the common neighbors for all these node pairs, use that formula. So 1 over the log of the degree of that common neighbor and summation of all these things. So degree of 2, or we have the value here, 1 over log degree. So so for node 0, these values that came from here, 1 over log degree, listed here. So 1 over log degree is this value. So you have to just sum them up. So for node 2, the value is 2.0959, and that's the only node in this intersection, common neighbors. So that's the value. Again, node 2, so 2.0959. Now it's empty set. So for if you don't have any common neighbor, the AIC score for the node pair is 0. So that's what we have here. So now for node 0, the value of 1 over log degree is 3.3219, and that is what we have here. And value for node 3 is 2.0959. For 4, it is 1.6609. For 4 and 5, so 1.6609 plus 2.0959 is 3.7568. Now for 3, 6, 7, so 2.0959 plus 2.0959 plus again 2.0959. So it is 6.2877. So that's the largest value among all the node pairs. So the first link is predicted to exist between 4 and 5. So now add this link 1, 5 and come up with the degree of the nodes. Okay. So the only thing that changed is the degree of nodes 4 and 5. So the degree of node 4 is now going to be 5. So these are the 5 neighbors, 2, 3, 5, 6 and 7. Now node 5 has 3, 4, 6, 7 as neighbors. So degree 5, so 1 over log 2. So let's say 1 over log 5. 1 over log 5 to the base 10. So log 5 is 1 over log 5, this is to the base 10. And then, so 1 over, so 1.43067. Okay. Now this is 1 over log 4, that is 1.6609. So now again come up with all the node pairs that don't have a link on this graph with one predicted link, and again find the common neighbors. Okay, so now 2, 5 has 2 has 0, 3, 4, 5 has 3, 4, 6, 7. So 3, 4 are the common neighbors. Again 3, 7 has 2, 4, 5, 4, 5, 6, so 4, 5 are the common neighbors. So now come up with the ASU score for each node pair. So with common neighbor just being node 2, the 1 over log degree value is 2.0959. Okay, so that's the ASU score. Now for 3 and 4, the 1 over log degree value is 2.0959 plus 1.4307. So sum of these two is 3.5266. And that's the largest among all the ASU scores. So the second link is predicted between 2 and 5. Now let us do the third link. So again, you have to account for the neighbors of nodes 2 and 5. So for node 2, now you have 0, 3, 4 and 5 as neighbors. For node 5, you have 2, 3, 4, 6, 7 as neighbors. So the log 4, 1 over log 4 is 1.6609, 1 over log 5 is 1.4307. So again, find for all the node pairs that don't have a link the common neighbors. So for 2, 6, for example, is 0, 3, 4, 5, it's 4, 5, 7. So 4 and 5 are the common neighbors. So now using the 1 over log degree values of these common neighbors, find the ASU score. So for node 0 it is 3.3219. For node 2 is 1.6609. For 4 and 5 put together 1.4307 plus 1.4307 is 2.8614. So the largest among this is 3.3219, and that is for the node pair 1, 2. So the third link is predicted between 1 and 2. So here we actually end up predicting only 3 links. Okay, so let us look at true positives. So we have 4, 5, 1, 2 and 2, 5. 4, 5 and 1, 2 are actually there. 2, 5 is not there. So true positives is 2 because 2 links actually exist. False positive is 1 because the 2, 5 that you predicted actually does not exist. And false negative is also 1 because the 3 links removed, 4, 5, 1, 2 and 1, 5. 4, 5 and 1, 2 are rightly predicted, 1, 5 was not predicted. So that's false negative. So now critical success index is 2 over 2 plus 1 plus 1. So it is 2 over 4, it is 0.5, much greater than 0.167 we got with the PAC technique. Now the precision is what fraction of the predicted links actually exist. So it's true positives plus false positives in the denominator, true positives in the numerator. So 2 over 2 plus 1, which is 0.67. Recall is what fraction of the links that actually existed and are predicted to and are expected to be predicted or actually predicted. So that is true positives plus false negatives, 2 plus 1, 3 links are expected to be predicted, and 2 of those 3 links are predicted rightly. So that is 2 over 3, so it is 0.67, and that's much greater than 0.3 and 0.25 that we got with the PAC technique. So now let us do the JSE technique, the Jaccard coefficient. Again, we have those 3 links removed, and these are the neighbors for the nodes in this modified graph. So Jaccard index is like for every node pair, it is the ratio of the intersection of the neighbor set of vertices and divided by union of the neighbors of the vertices. So on this graph, these are the neighbors for the nodes, and for these are the node pairs that don't have a link between them in this graph. So for example 0, 3, you just find the intersection and the union separately and then take the ratio. So 0, 3, the intersection is 1, 2 and 2, 4, 5, so it is just 2. Union is 1, 2, 4, 5, so it's 4 neighbors, 4 nodes. So you just worry about the size. So 1 divided by 4 is 0.25. For 0, 4, it is 1, 2 and 2, 3, 6, 7. So the intersection is just node 2. Union is 1, 2, then 3, 6, 7. That is 5 nodes. So 1 divided by 5 is 0.20. So you find the Jaccard coefficient like this for all the node pairs. For 4, 5, it is going to be 2, 3, 6, 7. For 5 is 3, 6, 7. So it's 3, 6, 7 as the common neighbors of the intersection. And the union is 2, 3, 6, 7, so that's going to be here. So the ratio is 3 over 4, which is 0.75, and that's the largest Jaccard coefficient value among all the node pairs. So the link is predicted to exist between 4 and 5. So now we add that link for 5, update the set of neighbors for each vertex, and go through the same process for all the node pairs. Find the intersection divided by union of the neighbors. So for example, for 3, 7, it's going to be 2, 4, 5 and 4, 5, 6. So 4, 5 is the intersection, and union is 2, 4, 5 and 6. So it is 2 over 4, that is 0.45. So 0.5 is the largest value, JSE value, and there are 2 node pairs that actually attain that value. So that means we say the second link is predicted between both 3 and 6 as well as 3 and 7. So we add both the links 3, 6 and 3, 7 to the graph, and we call it as right away graph with 3 predicted links because we actually predicted 3 links. Find the new set of neighbors for the vertices. Say for 2, 5 now you have 0, 3, 4 and 3, 4, 6, 7. So 3, 4 is the intersection, then 0, 3, 4 and then 6, 7 is the union. So that is 5. So 2 divided by 5 is 0.4, and that's the largest value among all the JSE values. And actually 3 node pairs are predicted to have those, not predicted, have those values. So since 3 node pairs have, we predict that all the 3 node pairs are predicted could have a link. So they are 2, 5, 2, 6, 2, 7. So we add all the 3 links. So totally we have now 6 links predicted. So using these values, we need to now calculate the performance metrics. So again, among the 6 links, 4, 5 is the only thing that actually exists here. 1, 2 and 1, 5 have not been predicted. So true positives is 1, false positives is actually 5 because you had 6 links predicted totally and only one of them actually existed. So 5 is the false positives, and 1, 5 and 1, 2 are not predicted yet. So false negatives is 2. So the critical success index is 1 over 1 plus 5 plus 2, which is 1 over 8, which is 0.125. Precision is true positives divided by true positives plus false positives, so 1 over 6, which is 0.17. Recall is true positive divided by true positive plus false negatives, so that's going to be 1 over 1 plus 2, which is 1 over 3, which is 0.33. So if you put together as a summary of all the link prediction analysis we just went through with the 3 techniques and the performance metric values, you see here the atomic adder coefficient based approach gives you the largest critical success index 0.16 and 0.5, 1.125. So 0.5 is the great largest. Precision again 0.67, 0.25, 0.17. So precision is again largest for atomic adder coefficient. Recall is also the largest for atomic adder coefficient. So all the values are at least 0.5 or above, whereas here you see all the values are less than 0.5. So as I said, for all the 3 performance metrics, we'll try to accomplish as close to 1. And in that sense, atomic adder coefficient is the best for this graph. Again, so the ranking of the link prediction techniques could be different for the graph. So for any other, for some other graph, the Jaccard coefficient technique would be the best of the 3, and so on. Okay.